My name is Lee Lind. I know most but not all of you. It's a pleasure to welcome you to the Jones Seminar Series, and you all can get a certain number of stars, I'm not sure in which scorecard, for actually having found this seminar at a different place and a different time than it normally is. So it's my pleasure to introduce Jeremy Faludi. Jeremy got a BA in physics from Reed College in 1995, a Master's of Engineering and Product Design from Stanford in 2003, and is now in the PhD program in mechanical engineering at Berkeley. And I don't always read sort of the full introductions, but this one strikes me as very interesting, and so I'm going to read it to you. So he is a lead accredited professional in building design and construction, and has been a sustainable design strategist and educator for over 15 years. He's taught sustainable product design at Stanford, Minneapolis College of Art and Design, California College of the Arts, and elsewhere. He's co-authored the Autodesk Sustainability Workshop, viewed by over 1 million people from over 150 countries, as well as Cradle to Cradle Products Innovation Institute's online learning program. He's contributed to 6 books on sustainability, including World Changing, A User's Guide to the 21st Century, as well as academic journal articles and technical reports for industry. Jeremy designed the prototype of AskNature.org for the Biomimicry Institute, and a bicycle he helped design appeared in the Cooper Hewitt Museum's exhibit, Design for the Other 90%. He was sustainability manager for Project Frog, one of the leaders in modular green building, and has consulted for Lawrence Berkeley National Lab. And he's one of the leading experts in life cycle assessment of 3D printing, the subject of today's seminar, and has consulted on the subject for Autodesk and the OECD. So welcome, Jeremy. We're very glad to have you with us.
Thank you. Thanks very much for having me. It's an honor to be here. And as Lee said, I do a lot of design, but I'm not going to talk about any of that today. I'm just going to talk to you about analysis, because sometimes you need to do a fair amount of analysis to figure out what your priorities are for design. And so I'm going to talk about green 3D printing, some facts based on research I've done, and myths, 2 popular myths that I'm going to dispel, some of which we were talking about at lunch, and then possibilities for the future of greener 3D printing based on other people's research. And just to talk about why this matters, industry as a whole actually is a huge source of environmental impacts. It's about 1/3 of the world's global CO2 emissions, depending on how you count it. And 3D printing is not yet a big part of the manufacturing industry, but it is growing exponentially. The manufacturing sector of 3D printing has actually been growing at 60% per year for the last few years. And so skyrocketing growth. And already, just for example, Boeing has 20,000 different 3D printed parts of 300 different kinds of parts in airplanes today. So you may have flown on a plane that has some 3D printed parts in the engines or something. And it's also showing up in mass customized products like custom hearing aids for people, or dental fillings, and other medical devices. And actually, like, how many of you in the room have used a 3D printer? Yeah, a lot. Excellent. That's great. So the way this talk is going to go is I'm going to start out with the actual research that I've done along with other colleagues and students of mine, starting out with a case study of a specific printer that we'll go more in depth on, and then after that look at all the other printers that we've measured in a more general way, and also compare them to a couple CNC milling machines. And then I'll dispel those 2 popular myths, and then finally get on to the positive hope for the future of possibilities of green 3D printing. And these are all the different printers that I will talk about later. I'll talk about most of them as they come up, but there's a very wide variety. 3D printing is not a monolithic industry. It's made of a bunch of different machines that work in very different ways, and they can have very different impacts. And the way that I measured the impacts is with life cycle assessment. It's a way of quantifying all the CO2 emissions and land use, water eutrophication, other things, which I'll show you a little later. And the thing that makes my studies unique is both the number of impacts that I measured, which I'll talk about later, but also the scope of measurement. Like, lots of people have measured energy use of 3D printing, but that's only part of the picture. And so I and my colleagues were the first ones to take this almost cradle-to-grave assessment. So it's not completely cradle-to-grave because we didn't look at the environmental impacts of what happens to the actual printed parts during their use phase, but that was because we were assuming that they would be equivalent to whatever other manufacturing method you would use to make that thing. And it was specifically because we're looking at prototyping rather than parts that are going into a Boeing jet. So for prototyping purposes, mostly people are looking at fit and finish. Is it the right size? Does it feel good to a designer? Things like that. But we did look at the embodied impacts of making the 3D printers themselves, so all the raw materials and manufacturing that go into the steel, aluminum, glass, electronics, etc. We looked at the transportation of the machines from where they are manufactured to where they're actually used, and the disposal at the end of life of the machine, and also disposal at the end of life of the parts that they print. And, of course, the energy use during the printing process. That's the thing that other people had measured before, but we combined this with the other ones. And then, finally, the embodied impacts of the materials being used in the printing process, as well as the waste that gets produced. And all the graphs that I'm going to show you quantify these environmental impacts per part printed. Because you have to have some kind of fair comparison when you're looking at one machine to another. And we tried printing a bunch of different kinds of parts. There are these solid apple shapes, these solid linkage shapes, these hollow apple shapes. We ended up finalizing on these for most of the printers that I'll talk about later, because this is the most common type of part that's being that 3D printers are being used for in design firms and engineering firms for the prototyping purposes. And then finally, we did this kind of part for the metal 3D printer, the one that I'm going to talk about in depth at first, because this is a more typical part for the aerospace industry, and that's what their printer mostly gets used for. But you won't see all of the printers compared to each other because we didn't print all of these parts on all the printers. Okay, so this is the first machine. It's a selective laser melting machine, and this is what it looks like. It's about the size of 2 refrigerators, kind of. And then there's some other auxiliary machines that go along with it, which are not pictured here, but which we also measured. And the way that we measured them is, first of all, with the energy use. To tell you how selective laser melting works is, it looks like this. You have a bed of powdered metal. In this case, we did powdered aluminum. And you hit it with a laser from the top. And it melts together the powder just where the laser strikes. So you can see all these areas where it's melted together, and then the negative space where it isn't. And so that gets you one layer, and then you have a little bar that wipes across another, microns thin layer of aluminum powder on top of this, and then you hit it with a laser again to melt it both to the parts next to it and to the layer below. And then that's how you build up layer by layer. So we measured the energy use of the machine using a standard Yokogawa meter. And we measured not just the printing energy, but also warm up, cool down, how much energy it uses when it's sitting there idle, because it does sit there idle for fair amounts of time, and all the auxiliary equipment as well. And then the trickiest part was measuring the embodied impacts of the machine, all the materials and manufacturing. So the best way to do this would be to take apart the printer into every single component material and then weigh all of those parts. And obviously, no one is going to let me do that with their, more than $1 million printer. So what we've done, and this was inspired by some other work done by in David Dornfeld's lab at Berkeley, is actually calculating the masses of materials by measuring the dimensions of things. Literally with calipers and tape measure and things to measure, this table is so wide by so long by so thick, and the density of wood is such and such, and so then can calculate the mass of wood in this table and do the same thing for the legs and etc. And then we use that to create a bill of materials with masses of all the different parts of the machine. And obviously this is super tedious, and it's not difficult, it's just really time-consuming and complicated managing the hundreds of different parts. And there is a fair amount of uncertainty here, of course. We double-checked our results with the published masses of all the different machines that we measured. And for this particular machine, we were within 3% of the published mass. So we were pretty confident that it was accurate, but we still considered it to have a large amount of uncertainty compared to the energy measurements, which are much more precise. And then the material is much easier to measure. Once you've printed a part, you can just weigh it, and that's easy. But then there's the material waste as well, which in this printer is a little trickier to measure because there's a lot of aluminum powder that doesn't end up in the final part. But almost all of that is just reusable the next time you print, and the next time, and the next time, etc. So for this, we actually relied on a previous person's study, Kellen's 2011, who had measured the waste and found that only about 4% of the powder gets lost in a particular print. And that's 4% compared to the mass of the final part, not 4% of the powder in the bed. And then for transport and disposal, these we just assumed based on where the manufacturing headquarters were of the companies that made the different machines and where the machine was being used. And so if it's being manufactured in China, let's say we assumed the certain amount of transport by ocean-going freighter and then trucking distance from the port town to where the printer actually was held. And this printer is in Nottingham in England. This is a partnership between me and the University of Nottingham there. And then for disposal of the machines and the printed material, we just assumed landfill for everything. And this is a conservative assumption because, like this machine, there's at least 2,000 pounds of steel in there. So that's probably going to get recycled rather than thrown away. But just for simplicity and sort of worst case scenario, because the thing is, with both of these impacts, they are such a minuscule fraction of the total life cycle impacts of the 3D printing that it really didn't even matter what we assumed. We could have been off by a factor of 10, and it still would have been insignificant to the total life cycle, as I will show you here. So these are the results for a particular scenario, and these are all the different kinds of environmental impacts that we're measuring with a particular methodology called recipe midpoint, or recipe midpoint H. And so you can see like the amount of climate change for the whole the printer and the energy use, the materials, the disposal, all that adds up to about 8 kilos of CO2 equivalent emissions per part printed for that particular little turbine part. And for ozone depletion, it was a very small fraction of a kilo of CFC11 emissions. Or for water depletion, whoops, sorry, I should quit that program. I'd forgotten about that. Okay, back on track. So for water depletion, the whole system of that product depletes about 0.1 cubic meter of water, and et cetera, for all these different kinds of measurements. And the different colors that you see here, the blue is the machine itself, all the raw materials and manufacturing of the steel, aluminum, et cetera. And you can see that it's a noticeable chunk. It's an important chunk of the full life cycle impacts, but it's not dominant for any of these categories except water depletion and metal depletion. And then transportation and disposal are so small you literally can't even see them on any of these indicators. You can barely see transportation here in urban land occupation and maybe one or two others, but that's about it. So like I said, you could be off by a factor of 10 and it wouldn't even matter. And keep this in mind for later. We'll come back to this point. And then the yellow here is the electricity use during printing and all the auxiliary devices. And so you can see that's the dominant impact for almost all of these things, everything except these two. And then the dark brown is the material use. That's the stuff that actually ends up in the part that was printed. And then the orange here is material waste, which again, you can't really see anywhere because it's just 4% of the material printed, so it's pretty small. And then the last thing is argon use, and that just shows up in water depletion. Any guesses why there would be any argon use for 3D printing here?
Building gas or lasers?
Well, I'll give you a hint. What's the material that we're printing in? Close. So powdered aluminum. Very, very flammable. Think thermite. Yeah. It's like explosively flammable. So yeah, we cannot have any oxygen in there when we're hitting it with a 200-watt laser. Yeah, so that's the only reason that we use that. And that will not show up in any of the other 3D printers that we'll talk about later. It's just so that you don't explode when you're printing in powdered aluminum or other powdered metals. But okay, so we've got these 18 different kinds of environmental impacts here, and that's nice for thoroughness. It's so that we can measure more than just, say, CO2 depletion or CO2 emissions, because some of these are very different. But if we're going to compare this scenario to other scenarios, other printers, or even running the same printer in different ways, it really helps to consolidate this into a single score. And there's various ways of doing this. The way that I like to use is called recipe endpoint H. And what it does is it's not just an average of all those other things. It's actually normalizing them all into a similar set of, the same set of units, which are just called points. It's kind of a meaningless term by itself, but it combines the environmental impacts of climate change, habitat destruction, human toxicity, ecotoxicity, and resource depletion, all into a single metric. And you might think that's a hard problem, and yes, it is a hard problem. And no one has really agreed on one universal way to do that. I chose this particular method because it's one of the most credible and most widely used, and I think it does the best job. But there are other systems that work in different ways as well. But so, again, that consolidated all those bars from the previous graph into this one much simpler graph that gives us a single set of priorities. And it's basically what we saw before, where the energy use is by far the dominant impact, and then the impacts of the machine itself, and the material used, and then a little bit of the waste. And that's because... So the reason I did this again was to compare it to other scenarios. This scenario here is when the printer is printing at maximum temporal and spatial utilization, which means it's printing 24 hours a day, 7 days a week, and it is printing a full print bed full of parts, because it can print multiple parts at once. And so this is full spatial utilization, because that's about as many as can fit, whereas we also ran the scenario where we just printed one part at a time. And we also changed the temporal utilization, because most 3D printers do not get used 24 hours a day, 7 days a week. I mean, how often do the 3D printers you guys have on campus get used?
Quite a lot the week before the project's due.
Yeah. Okay. Well, 8 hours a day is great. That's a high utilization compared to some places where, it's a design firm and they have a printer around for prototyping, and they'll use it once a month or something. Okay. Yeah. But yeah, just to give you an idea how much the utilization matters, that bar that we were looking at earlier is this one down here. Okay, and so if you compare that to just printing one part per week and then leaving the machine on the rest of the time, so that it's ready at a moment's notice for you to print something else, and only printing one part at a time rather than a full bed worth of parts, your environmental impacts go up by a factor of 15, basically. And so obviously the energy use explodes because you are sitting there idle a lot of the time, and that uses energy. But also the machine's impacts explode as well, because you're no longer amortizing away the embodied impacts of the printer by printing lots of parts. You're not dividing it by the number of as many parts that you've printed. And then there are these other scenarios that are in between, like if you print one part per week but you turn the machine off when you're not using it, then the machine impacts still don't get amortized away, but at least you don't have tons of idle energy. And so how you use your 3D printer matters a lot for the environmental impacts. And just to compare this to other manufacturing methods, and this is more of a sort of back-of-the-envelope comparison. This is not in any of my publications. It's just something that I did for benchmarking. Looking at the scenario from earlier, printing 24 hours a day, 7 days a week. So again, this is this bar down here. And I'm just changing the error bar to a fade. It's a little easier to read. So comparing that to lost wax casting, we can see that the impacts are on par, roughly. It may be a little worse, but they're within error bars of each other. And this is the one that's the most fair comparison, because lost wax casting is another thing that you can do complex geometries in, whereas these other things like sheet rolling or extrusion, you just can't make all the shapes that you can with a 3D printer. And so, arguably, these are not fair comparisons, except that I have seen people, like students at Berkeley, 3D printing something that is a flat plate, just with a cut-out contour, because it was more convenient than ordering some material and cutting it and whatever. So even though it's not really a fair comparison, it can sometimes happen. Okay, and LCAs of other devices here. So these are the 7 other kinds of 3D printers that we measured. And as I said, they work in different ways. So these 3 here are fused deposition modeling, FDM machines. And they're basically a plastic extruder. It's like a hot glue gun with XYZ control. These two are the small desktop jobs, and this one is a larger commercial version. What kind do you guys have here?
FDM.
And are they like small desktop? Or?
Big one.
Yeah, okay. Is it a dimension?
It's bigger than that. I think we have a dimension, but we also have an even bigger one.
Okay, cool. Okay, cool. Yeah. So this is the object here for those of you that haven't seen it. And this, and this work in a different way, where they have an epoxy, a liquid epoxy that is activated by ultraviolet light. So it's liquid until you shine UV light on it, then it solidifies irreversibly. It's not like these FDM machines where you could just grind down the plastic and remelt it, re-extrude it. And then even these three, they work in different ways. So this one here is stereolithography. It's got a bath of that epoxy, hits it with a UV laser from the top to solidify. This one here is a DLP. It's a digital light projector machine, and it has a very thin layer of the liquid epoxy, and it hits it with a projector from underneath, very similar to this kind of projector here. It's just with a UV LED instead of a 3-color system for making pretty pictures. And then this one, the PolyJet, it has it's sort of like an inkjet printer in that it prints out this liquid epoxy only in certain places and not in other places, and then it has a big UV lamp behind the print head that comes along and shines light on it just after it's been printed out, and then builds up layer by layer like that. And then the last one here, this is an old Z-Corp machine, and this is more literally an inkjet printer in that it actually uses old desktop printer inkjet cartridges to print a liquid binder into a bed of powder. So it's kind of similar to the selective laser melting machine in that there's a bed of powder, except it's not metal. It's usually a kind of plaster, sort of. And then you chemically bind it together with this liquid. Oh, you do? Oh, awesome. Is it one of the newer ones, or? Cool. Well, that gives you some interesting opportunities because the one that I actually measured here was one that had been hacked by Professor Ron Rael at UC Berkeley to print not in the standard materials, but in things like sawdust, salt, coffee grounds, all sorts of things. So the measurements that I did of this one were for printing in salt. Yeah. And these are the two CNC Mills that we compared them to. So for both of these, we started out with a block of ABS plastic because that's a common plastic that's used in FDM. So started out with a block of ABS and then cut away everything you don't need. This was a smaller machine. It's a Mori Seiki, and then the larger Haas VF0. And for all the stuff that I'm going to show you here, the functional unit is this particular part because in order to compare one machine against another, you really need to make sure you're doing an apples-to-apples comparison. So that was why I did that. Thank you. And so these are the results. So each line is a different printer. And some of these we use different materials as well. With the FDM printers, there was the Dimension FDM printing in ABS and one of the desktop ones printing in ABS, one of them printing in PET and PLA instead. So PLA is a bioplastic that has significantly lower environmental impacts than ABS and has a lower melting point, which means you don't need as much energy to print it. And then the DLP, that was the light projector one. It was one of the UV epoxy ones. This is a small desktop one by Autodesk. And then the PolyJet that we mentioned. And SLA is the third epoxy one. and then the inkjet of salt, which you can see as tiny, tiny impacts compared to almost everything else. And then the two CNC mills down at the bottom here. And also note these four here that have two bar graphs. That's because we thought it was worthwhile to run different scenarios here. We actually did lots of scenarios of all of these, and this is just a single representation of maximum utilization, printing 24 hours a day, 7 days a week. But then these three printers also allow you to print multiple parts at the same time, like the one that we saw before, and that radically improves your environmental impacts per part. Whereas all these machines, they can't really print more than one part at a time, or if they did, it wouldn't change the environmental impacts of them. And same with the mills. And the reason for the two bars on the Morisaki mill, the small mill, are basically because the machinist who was operating it took what we thought was an insanely long amount of time to do all the fixturing and flips and things. It was a different machinist than did this one. It was not me, and it was not a student. It was they were professional machinists. So I'm not going to say that there's error in there. But we thought it was worth looking at what if the scenario were more like what the other machinists did as well. So a few conclusions that you can see from this is, first, that there's a huge range of impacts from one printer to another. And a lot of them are, in fact, better than the two CNC mills that we compared them to, but not necessarily. Like the PolyJet here, if you're printing one part at a time, it is well within error bars of the Haas CNC mill. And this scenario for the Morisaki. And even though there's a lot more material waste in the mills, because obviously you're starting with a chunk of material and cutting away most of it, the total impacts are on par with this machine, because even though there's less waste, there's more energy use. But then for other printers, there are very low impacts in comparison to machining. Particularly the desktop FDM of PLA plastic works out really well, both because it's a green material and it's a lower energy process. And then the best one was the inkjet of salt if you're printing multiple parts at the same time. And just to sort of simplify this again, because we're going to make it even more complicated, I'm going to put it back into this style graph where, again, I'm just blurring from the bottom to the top of the uncertainty range. And I'm adding injection molding of ABS here. And so if you thought that this earlier comparison was saying that 3D printing is almost always greener than other kinds of manufacturing, well, you might be right for machining, but not so much for injection molding. And this was data that we didn't empirically measure. This came from EcoInvent database of the LCA software that I use. So you could take this with a little grain of salt, but even if it's off by a factor of 2 or 3, it's still giving the same conclusion. And if we zoom in a little more, you can see more clearly here the comparisons where at the high end of its uncertainty, it's on par with the low end of desktop FDM of PLA plastic, which so you could say that is an eco-friendly way to make things. Although it's not really a fair comparison because this is ABS plastic, and you can injection mold ABS plastic. And if you do, these impacts will shrink. They will shrink to below that. So really, the only one that will absolutely win over injection molding is the bottom end of inkjet printing in salt. And then if you're at the high end of the uncertainty there, then it will still not win. It will be up to like a factor of 2 worse than injection molding. And so it just depends on how you're operating the machine, what materials you're using, and what you're comparing it to here.
Is it use of self-comment, or you implied it was a one-off kind of thing that was
Yeah, no, this is a hack by that particular architecture professor. Yeah. They're, in fact, these companies actively discourage you from using different materials because their business model is usually razor and blade kind of. They sell you the expensive materials. And that was why I asked whether you had an older machine or one of the new ones, because the new ones are harder to hack. So whether 3D printing is green or not really depends on what kind of printer you're using and compared to what other manufacturing method and what specific product you're printing to. Remember, I showed all these different parts here. Having a part that is mostly a hollow shell and that it's a really complex material, that really favors 3D printing versus CNC milling, because this part here performs much better for the CNC mill. Not only is there a lot less waste because it's a more solid part, but this is operationally very simple for the CNC to do. And so that reduces both the material waste and the energy use. And it increases the energy use of a 3D printer because there's more material being printed. So again, it depends on a lot of different things. And then, of course, there's the utilization question as well. So the graph that we had a second ago is printing 24 hours a day, 7 days a week. But as we saw before, utilization really matters. So this is printing one part per week and idling the rest of the time. And you can see that even the best performing printer before, these two, are now way above the worst of the printers. Printing 24/7. And then to zoom out the graph so that you can see the rest of these bars, it's such a huge difference that you can't even see the original bars except in a couple places. So, and this can be up to a factor of 40 difference in environmental impacts per part. So utilization really matters. And those are the bottom lines here, the 3D printing facts, is that there's a huge range of impacts, and energy use dominates, but utilization is super important. And some kinds of 3D printing can be very low impact, but they're mostly these experimental materials, like printing in salt, or green material enabled like the PLA desktop machine. And it also depends on what kind of process you're comparing it to. So really, you have to go product by product as to make an intelligent decision here. Okay, so those were the facts. And then you use those to dispel a couple myths. There are really two big myths that get bandied about a lot with 3D printing. And the first one is that 3D printing is inherently green because there's no waste. And guess what? That's not necessarily true. There are some where it is true, like the metal printer that we looked at before. There's very little waste. And some FDM machines, if the part that you're printing doesn't have any overhangs that require support material, then that can be very low waste. But then there are other machines like the PolyJet printer, which wastes 43% of its liquid epoxy before it even gets to the printed part. And so that's not even counting support material. So you could easily have more than 50% waste out of this printer if you combine both the inherent waste and whatever support material for overhanging parts. And then you have to keep in mind that other manufacturing methods, like, yes, CNC milling has a lot of waste, but injection molding normally has very small amounts of waste, depending on the geometry that you're printing. And so 3D printers may or may not be saving that much compared to injection molding. And even if they were, it's really the energy use during the printing that is the most important thing. Like, remember, comparing the CNC mill to the PolyJet printer, even though there was less waste in the PolyJet, they scored about the same with an uncertainty because the PolyJet used a bunch more energy. And so it doesn't really help if we're eliminating waste but adding more energy impacts. We have to look at the whole system. And then the second popular myth is that 3D printing will eliminate transportation because you can just print things at your desktop. And people seem to forget that the materials that you're printing with have to come from somewhere. Now, you certainly can save some material, or you can save some transportation by, if you're an auto parts store that makes 100 different parts out of the same material, you don't have to carry as much stock. You can just have the raw material. But again, even if this were true, it doesn't really matter much for most products. You saw before that transportation in this particular situation was a vanishingly small percentage of impacts. And that's true for a lot of products. It was even smaller here than it is for most products. Most products, it's at least a few percent, maybe 2 to 10%. And every now and then you get a product where the transportation is a dominant impact, but it's super rare. Of the dozens of products that I and my students have done LCAs of over the years, there's only been 1 or 2 where transportation was the dominant impact. Okay, so then on to the possibilities for 3D printing. This is a super fun thing. It's Marcus Kaiser, his solar sinter. So what he has here is he has a giant Fresnel lens focusing the heat of the sun onto this bed of sand and fusing it into glass. And then, and then solar panels to run the electronics, the motors and stuff. And so here, he actually is eliminating transportation because he is just scooping sand up from next to the printer and sticking it right in the print bed. And 100% renewable energy and local, non-toxic, abundant material. So that's all great and fun. I don't think this is going to scale to real industry manufacturing, but it's a really fun stunt. But what could potentially scale is the sort of stuff that Ron Rael is doing with a hacked Z-Corp printer. So this is a part that he printed in sawdust. And it's a green material. It's a renewable material. It's abundant. It's a waste product, in fact. It's low embodied energy. It's non-toxic, compostable at the end of its life. Pretty much everything that you would want out of a green material and in a circular economy. And the processing of it, the printing, is very low energy as well because it's a chemical binding process. You're not melting plastic. And this also illustrates another important possibility of green 3D printing, which is that complexity of design is almost free, whereas it's the materials that are the expensive part. And similarly, the processing time to print is expensive because it can take hours and hours to print a part, and time is money. And that printing time is proportional to energy use. Not necessarily between printers, but when you have a particular printer, the shorter the print job, the less energy use. And so what this does, it aligns the economic incentives so that the things that make sense financially also make sense environmentally. And I think that's a very strong long-term trend, even if it hasn't pushed the industry very far yet.
Is there an additional binding agent that's used with the sawdust in this process?
Yeah, there is. I forget exactly what it is. It's a little, partly isopropyl alcohol, partly some water, and I forget what else. But even the binder is pretty non-toxic. Yeah. And also with 3D printing, because you can do it at any time, it discourages overproduction because you don't need to order 100 parts 2 weeks in advance. You can have parts printed just in time. And another variation on cool materials and printing processes is closer to you guys, right over at MIT. This is water-based digital fabrication. Have any of you guys seen this, by chance? No? I haven't seen it in person either, but it sounds cool. And so this is similarly using a very green biomaterial. They're using mostly chitosan, which is kind of ground up shrimp shells. It's a waste product from the food industry. And there's some water and a couple other ingredients. And so again, abundant, non-toxic, compostable material with low embodied energy. And it's a low energy process, so they just extrude it as a paste, and the binder evaporates away. It's like glue drying. And so again, it's not having to melt material, it's low energy. But then the other interesting thing about their process is that they also can get multiple different material properties out of the same ingredients. So even still just using chitosan and water and a couple other things, they can have the material have a different strength and different flexibility, different Young's modulus, under one set of printing properties and a different set of Young's modulus and strength in a different part of the same print job. And they can go continuously in between, so you can have a continuous variance. And that opens up all kinds of interesting manufacturing possibilities that we can't do with normal manufacturing, and might allow us to make more complex products put back into a circular economy by having them all be compostable, because even though they're different material properties, they're all still the same ingredients. And then there's the question of use phase energy. I mentioned the different parts being used in Boeing airplanes before. This is a jet engine by GE where they've used a bunch of 3D printed parts to get more optimized geometry for the nozzles for their fuel injecting, and they say, and they also allowed it to use a higher temperature ceramic, metalloceramic alloy that they just could not manufacture with before. And so they've said that this has allowed airplanes to increase their fuel efficiency by about 15%, which saves millions of gallons per year. And at that point, it doesn't even matter if the manufacturing stage is more impactful than traditional kinds of manufacturing, because that will all be lost in the noise compared to the use phase impacts of an airplane that, lasts for 20 years and flies millions and millions of miles. Then there can be social benefits as well, potentially. 3D printing has the possibility of democratizing production. This particular photo is some people bringing a 3D printer to some of the poorest of the poor rural village in Haiti to print out umbilical cord clamps that they have not traditionally had a supply chain or distribution network for. And that's cool. It's a good idea, although I have to say I don't think that is going to scale, because if this village doesn't have a supply chain or distribution network for a simple plastic part, it certainly does not have a supply chain for a $3,000 laptop or the RAM or hard drive that you would need when this thing breaks down in 5 years. But I think that there is a lot of potential for 3D printing entrepreneurship in cities in developing world, where there is a supply chain, there is a distribution network of industrial goods, and what you can do is, 3D. The whole benefit of 3D printing in prototyping is that you can make one part. You can make 10 parts. You don't have to spend $50,000 on tooling to work up to injection molding. And so that's a nice to have in rich countries, but in developing countries, that can be huge because it can replace venture capital. You don't need to get a loan to start your own business if you can just print one part at a time, sell that, make 10 parts, sell those, and work your way up to the point where you've made enough money that now you can spend $50,000 on tooling for injection molding and get your business off the ground. So no one has studied that yet, but I think people should, because I think that's the place where it has potential for developing economies. And this is also the way in which local manufacturing matters. It's not so much the environmental impacts of transportation, it's keeping your revenues, keeping your profits local for local businesses. And then the final possibility for green 3D printing, I think, is in repair of legacy products. So this is a website called Thingiverse that is full of CAD models that you can just download and 3D print. And so this is a dishwasher wheel clip. So imagine if you have a 10-year-old dishwasher and this part breaks. Well, are you going to throw away your whole dishwasher for just this stupid little plastic part? Well, instead, you could go to Thingiverse, and you could download this part, 3D print it, and then snap it back in there yourself. Now, I don't know how much this is ever going to scale, because there's not a huge culture of repair in America. It would be great if there were more. And by and large, and there are also intellectual property concerns here as well. Like, most of the stuff on Thingiverse is totally legal, but they have been sued for IP infringement because a company is like, I forget if it was I don't think it was a dishwasher company. I think it was someone else. But you know, the dishwasher company could say, hey, that's our part. You don't have rights to that. And I think they did win the lawsuit, but it's still not a clearly defined area. Okay, so just to sum up here some of the possibilities, I think the most powerful one is the potential to align the economic incentives between the environmental impacts and what makes money. And then optimizing the use phase, so for things like airplanes and cars, where the vast majority of the impacts are in the use phase, then you can do whatever you want in manufacturing almost and still save impacts. Possibly democratizing production, this should be studied, and possibly enabling new materials like sawdust or salt or things. Who knows, maybe some of these materials might even feed back into more traditional kinds of manufacturing. And then possibly enabling repair as well. So there's a lot of work that still needs to be done in this area. So you saw how much variation there was in the environmental impacts from one printer to another, from one material to another, and comparing that to what it would replace and the utilization. So the NSF's 2009 roadmap for additive manufacturing suggested that full LCAs, like what I've done here, should be done on basically every kind of printer out there. And that's a long way from being true. And once we've done that, I think we also need to compare to the other manufacturing types that they would be replacing. You know, how does it really compare to lost wax casting or extruding or other things? And then finally, we need more development of greener 3D printers. That's not the direction that the industry is going these days. They're just trying to make as much money as they can and get as much market share as they can. But I think with the right focus, we could really steer the industry towards greener materials and lower energy processes that would slash their environmental impacts. And if you want to know what to do with the 3D printers that you have today, that are sitting in your labs, these are the suggestions that I have to make your existing processes greener. So share machines, because you saw how much utilization matters. So try to keep your machines, rather than buying more machines or having, you know, a printer on every desk or something like that. That's a terrible idea. Heck, that's a terrible idea for 2D printers, much less 3D printers. But yeah, so have a small number of machines, but keep them running as much as you can, and share them with as many people as you can, both spatially and temporally. And then try to encourage good processes and materials. So for an FDM printer, use PLA plastic rather than ABS, both because the plastic itself has fewer embodied impacts and less toxicity, but also because it lets the printer run at lower energy. And if you've got the Z Corp, you can hack it to print in awesome materials. And then finally, optimizing geometries. So reducing the amount of material in your prints, reducing the amount of support that you need to print it. And so I have actually done some design work in this area, but I can't show it to you because it was for Autodesk. But I've been helping them to try to make better software tools, better print drivers that can help people automatically optimize part geometry and share machines over the internet and among multiple users. And well, one thing that I can share actually, so their printer was the DLP printer, and when I first analyzed it, it used exactly the same amount of power when it was sitting there idle as when it was printing. It used 50 watts, whether it was printing or not. And when I pointed that out to them and suggested some changes, they were like, "Oh, holy cow, that's embarrassing." But a year later, just a few months ago, they brought me back and said, "Hey, we've done some design changes. Come measure it again and see how much we've improved." And I'm very happy to say that they reduced their printing energy by 20% and their idle energy by 80%. So yeah, so that's great. And they did it just with software and firmware changes. They didn't even have to change any hardware. So that is mostly it. Here's some papers that I've done on the subject if you want more technical detail. And for acknowledgments, I'd like to thank David Dornfeld, who recently passed away, but who got me started on this whole green 3D printing kick. And then some of this work was not funded, but some of it was funded by Autodesk, some of it was funded by an NSF Eigert Fellowship, and a little bit was funded by the OECD. So that's it. Thanks very much. Yeah.
So two related questions. What parameters do you need to change to get different properties out of Kaizen? And can you do that in your CAD software and say, I want this part to be like this and that? And then a related, bigger picture question. Standard manufacturing now makes many little parts and then assembles them to be robotic assembly. If you have a 3D printer that can give different properties to different areas, or perhaps even use different materials for different areas, you could imagine printing a whole complex assembly all at once. Do you see that scenario being fulfilled in the future?
So yes, definitely. For your first question, I have to say I don't really know. I know that they have a same set of ingredients and they just have changed the ratio of ingredients, but I don't know how they control it. I've never been over there to talk with them, so I don't know if it's a CAD parameter or if they have to do it more manually or what. But in the future, if you were developing a tool to do that, you absolutely could build that into a CAD tool, or what it would more likely be is it would be your printer driver software. Yeah, so you'd import a CAD model and then you would do transformations on it. But to your second question, yes, absolutely. The industry is already moving towards multiple materials printing. So in fact, that's one of the main reasons that most people get PolyJet printers, is because they can already print multiple materials at the same time, and those can have different stiffnesses, different strengths, different colors, different. Some can be translucent or transparent, others opaque, and all kinds of things. And also at MIT, Neri Oxman has done some fun stuff with just PolyJet of multiple materials, and that is inevitable for the future because, yeah, that's what industry wants, because that would save money in assembly. Now, normally that's an environmental nightmare because suddenly you have all these dissimilar materials that you can't separate. And that's why I was strongly pushing biomaterials and compostability, because then you don't need to separate it. It doesn't matter. And in fact, even today, composting is a cheaper end of life than recycling for most things. So yeah, I think that's an area that needs a lot more development and would be a great research area.
You can imagine a reverse 3D printer the exact extracts the material and put it down.
Totally, yeah.
To what degree is there any relation between the total cost per part and the environmental impact?
Almost none. Yeah, I mean, there's a little bit, because like I said, the more material you use, the more it costs money. And materials, a lot of these materials are expensive. And so people are at least somewhat motivated to save materials.
I mean, maybe across machines.
Yeah. Well, that is something that's even true across machines, because so many of them use the razor and blade business model. Yeah, the energy use is much less correlated from one machine to another. You know, a lot of these desktop jobs, they'll only use like 50 watts of power, but then some of the bigger ones can be like 700, 800 watts. And nobody cares because electricity is cheap. But once you have a particular printer, you are motivated to reduce the print time because print times are long.
One other difference I've noticed with 3D printers versus more traditional techniques is that they break down a lot. There's a lot of maintenance, there's a lot of service, a lot of failures, and the level of expertise, training, education required to get them running again and to use them well and creatively is very high.
Yeah.
How do you begin to think about the cost of human capital, training, maintenance, lost opportunity, all those other factors that come in?
Yeah. Well, first of all, that's another reason that I don't advocate a printer on every desktop, but have much fewer printers that are shared by many people, because then you can afford to have a trained professional administering it so that it doesn't break down all the time, and so that you don't give it stupid print jobs that are going to fail just because, you know, they're not optimized, or, you know, you oriented the part badly or whatever. So part of that is going towards more sharing of printers. But yeah, this is another unresolved question about the social sustainability of 3D printing, because yes, it does require more skilled labor, but it requires a very small amount of that compared to the amount of unskilled manufacturing labor that would be used for hand making something or hand milling things. And that's something that I haven't seen anyone study. And so I don't have a good answer for you there, but I think it needs research. Yeah.
Two questions, you can answer either one.
Either one, take them up.
I was thinking about, like, you were showing the turbocharger, and there's companies that make those that probably do it with a sand casting, an assembly line, and they make thousands of them. And so I'm wondering if do you see 3D printers in the next, or could you scale it up to be like the size of a factory, where like that picture you have on the screen could be like the size of like this room or a football field in size, so you're making thousands of parts with one print job?
Yeah, and people are trying to do that. It's going slowly because, as you pointed out, it's still pretty error prone, and ruining a batch the size of this room is a much bigger problem than ruining a batch this big. But yeah, there are people working on how to scale it up. And in fact, Google's Ara phone, their modular phone, was mostly held back. The reason that it sort of failed to ship in time was in part, not entirely certainly, but in part due to the fact that they wanted to use more mass manufacturing scale 3D printing to make the parts, and the company that they were working with couldn't get it to work well enough.
Okay, so the other question was, you mentioned the aircraft engines and they can 3D print in the ceramic and that enables higher temperatures, more efficient engines. Do you have other examples of things that just can't be done with other manufacturing, like this is going to enable other technologies? That seems like a really, really important area of your research, if we can devise other places where this enables.
Yeah. Well, and there's a lot of things that people make that they say can't be made in any other way, but it's really a question of, can it be economically made any other way? Because even some of these fancy, funky, on a more household level, there's the jewelry of Bathsheba Grossman, who does these super cool topological mathematical models that are all interwoven, that she 3D prints in metal, and they supposedly cannot be made in any other way. But if you really wanted to, you could make all the different parts of those things by casting or machining or whatever, and then weld them together or glue them together, things like that. And it's just a question of, would it be economical, and would it have the strength or other material properties you need? So, yeah.
Oh, I was just going to say they're 3D printing biomaterials and organs and graphene.
Yeah. So those could be good examples. Those are things that are hard to manufacture in other ways. Yeah.
Yeah, so I think on like your second or third comparison slide, you compared 3D printing plastic to CNC milling plastic.
Uh-huh.
And if I remember right, it made...
This one?
Yeah, so it made pretty much all the 3D printing processes look less costly than CNC milling right now.
For this particular part.
Okay, sure. Now, it seems like a more direct comparison would be comparing CNC milling of metal to like that selective laser sintering, like what you talked about in the beginning. Have you done that comparison?
I haven't. I would like to, and in fact, I would have loved to have done that half apple part on the laser sinter machine, but you know, it wasn't my printer; it was their printer, and they wanted to make the other part. So yeah, that was kind of how it went. But yeah, I would like to do those comparisons, but I haven't been able to yet.
Do you think that maybe it would be shifted? Do you think this trend would replicate, that it would still be cheaper or less costly to do it through a like SLS or SL, whatever you call it?
Yeah, selective laser melting. I'm trying to remember what the total energy was for the SLM machine per part, just to try to remember whether it was on par with this. I mean, the funny thing about CNC Mills is that it doesn't actually matter that much what material you're milling in terms of energy use. So the mill uses a fairly similar amount of energy no matter what. But yeah.
Okay, yeah. Thank you.
Yeah.
It seems like a lot of what you're talking about was the present use in prototyping. And then there are examples like the jet engine for production. There's also this concept that we won't have Walmart anymore. We'll just have, instead of driving to Walmart, you'll walk to the kiosk in downtown Hanover and pick up the part you ordered 5 minutes ago. And it seems like a lot of what people are talking about when they're talking about the myths that you dispelled are transforming the whole economy, so we move away from manufacturing to doing it that way. And I'm wondering if you could comment on whether there is a possibility of that in the future and what the impacts might be.
Yeah, we are a very long way off from that happening. Yeah, like maybe optimistically 20 to 50 years. I don't know. I mean, that's just a rough guess. But keep in mind, the reason that I say it's so far off is that, you know, most products that we have, they're not just one part. You know, it's not just PLA plastic. You know, there's probably 10 or 15 different materials in here doing different things. You know, and there's the ink and the different kind of plastic and the metal, the roller ball, and all that kind of things. Very few products are just a simple plastic part. Like, okay, this you could go 3D print today, and that's fine. But that's pretty rare. You know, the table, the chairs, you know, your tablet, you know, your phone. All of these things are complex assemblies of lots of different stuff, particularly anything that has electronics in it. You know, we're a very long way off from being able to print, 3D print a CPU for, anything, right? And that's something that a lot of the like really gung-ho supporters of 3D printing tend to forget is that yes, you could print a stapler in a 3D printer maybe 10 years from now. You're nowhere near doing that today because there's the metal here and the plastic, and very different materials requiring different processes, and you still have to assemble those parts. You still need some assembly labor and things like that. Those don't scale well. There's still, if you were 3D printing and hand assembling a stapler, it would probably cost you $5,000. And so it's going to be a long time before that is a thing.
Let's thank our speaker.